And if you have any questions, just put stuff in the chat. All right, so last time we talked about the introduction to the atom, all right? So I want to like put together like some ideas here, stuff that we've done in the past with the introduction to the atom, all right? So this is what we're going to do. We're going to start with two terms. We're going to start with the term, matter and energy. So these are two terms that you should be pretty familiar with. Sorry, I have a question in the chat here about the last recording. I think it was Eleni. Yes, the last one was recorded. Yeah, I recorded the last lesson too. Okay, so it should be posted in Schoology. Okay, so matter and energy, right? I mean, these are two terms that you should be familiar with. If you remember, they actually came up in ecology when we talked about how these two things actually get cycled. We talked about like the water cycle. We also talked about the flow of energy. Now, what are these two things? So like, you know, we use these terms. Matter, we know, are things that take up space, and you can measure them on a scale. They, you know, made up of stuff. They have mass, for instance, right? You can put them on a scale and measure how heavy they are. And energy are things that we know that give us the ability to, like, for example, to move, right? Like heat is an example of a type of energy. So we're kind of familiar with these two terms, and they came up in ecology because, you know, things require both. They require matter and they require energy, right? Growth. When you grow, you acquire material, matter by eating, but you also need energy to grow. Okay. Now, when we're looking at the atomic and particle theory, you know, we can say that matter itself is made up of like particles, right? Remember, this term came up. Now, what are particles? Okay, so particles is a term that we can kind of use to describe two things. On the one hand, we can say that they describe things called molecules, and I'm going to distinguish the difference between the two. And on the other hand, atoms. So particles can mean molecules and they can mean atoms. Sorry, it's a question in the chat. For some reason, the questions don't come up all the time. I don't know why. Okay, so what's the difference between these two things? So an atom is basically, you know, one thing. Like it's, for example, like an atom of aluminum, right? That's an example of an atom. Or we can say an atom of carbon, okay? That's an example of an atom. A molecule is made up of two or more atoms, okay? And if they are different atoms, then we're going to call it a compound. So if it's the same, if they're made up of the same thing, then we call these things elements. And that's, you know, where do you see these? You see them on the periodic table. So last time we talked a little bit about the periodic table. Okay, so if they're made up of the same type of atom, that's an element. All right, if they're made up of two or more types of atoms, that's a compound. So for example, aluminum is made up of aluminum atoms. They're all the same. Carbon is made up of carbon atoms. They're all the same. But water is made up of two things. It's made up of hydrogen and oxygen. It's made up of two different types of atoms. So that's a compound, okay? So here's the terminology, right? A particle can mean a molecule or an atom. A molecule is two or more atoms, and if the two atoms or the atoms that are in the molecule are different, we call that thing a compound, right? Whereas an element, all the atoms are the same. All right, we're just going over some some basic terminology here. Okay, now we've been looking at the atom. That's what we talked about last time. So if we take a look at atoms, we said that we can take an atom, we can divide it into three things, right? So we last time divided them into three things. One is basically the two particles that are in the nucleus. And the other one is the particle that exists in the orbits around the nucleus, right? And these would be then your protons and your neutrons in the nucleus. And the ones that are out in the orbits are your electrons, right? These are the three particles or subatomic particles that make up the atom. We talked a little bit about each one. So for example, we said that the proton is positively charged, the neutron has no charge, and the electron is negatively charged. We also said, even though this is not technically true, we also said that the electron has no mass and that the nucleus is really the only thing that provides what's called the atomic mass, because the only things that are considered to have mass are the protons and the neutrons, and they're considered to have a mass of what's called 1 AMU. AMU stands for atomic mass unit. It really, okay, it's kind of like what, mass. Normally you think of a unit of mass like as kilograms, or a unit of distance as in meters, or a unit of time as in seconds. An atomic mass unit, what's really important for you to understand what that means is that the proton and neutron are both 1 AMU. So that means that they have the same mass. That's what's important, okay? Not exactly what is exactly an atomic mass unit. You don't need to know that. Just know that they're the same mass, and that those two things will give the atom, the atomic mass. We also said that the atomic number is just simply the number of protons. This is what we talked about last time, okay? Now, so we also said that the atom itself, so I'm going to draw a line here. The atom itself is, if you remember, made a comment that it's actually mostly empty space. The nucleus takes up a very small amount of space, and then the rest of it is pretty much empty space. Just to give you an idea of how small an atom is, so the atom is considered to be about 10 to the minus 10 meters. Now, what does that mean? That would mean like something, if you were to put that into context, you could, at that size, you could fit about 1 million atoms across a human hair. So in other words, it's about 1 million times like thinner than a human hair. So that's how small that is, right? It's very, very tiny. And most of that is empty space. And just to give you an idea of context, how much of it is empty space, imagine that the atom is, imagine the nucleus is the distance from, let's say, SJMP to Finch. Let's say that's the nucleus, okay? The width of the atom, or the radius, or sorry, actually the diameter of the atom, would be the width of Canada. Think about that for a second. So and this goes back to Rutherford's gold foil experiment. You bombard gold with radiation and most of it goes right through because the nucleus is a very tiny thing. It's basically just simply the distance from SJP to Finch. It's about a kilometer. That's about a kilometer. Whereas the atom itself, which is mostly empty space, is like the width of Canada, which is about 9,000 kilometers. It's kind of crazy when you think about that, right? Put it another way, if we were to take all the space out of an atom, if we were to do this and crunch it down, you, a human, would be about the size of a grain of sand. Which means that you're mostly empty space. Now, this is nice because, we're kind of tying in some ideas and some terminologies and kind of getting a picture of the atom and its size. We also tied it a little bit back to ecology, and we talked about cycling of matter and energy. But we can also tie this now to space, because if you recall, we talked about, in space, we talked about like a neutron star. So a neutron star is called a neutron star because what happens is the atom is only made up of neutrons. Now, what does that mean? That means there's no protons and electrons. What happens is the atoms, electrons, get squeezed into the nucleus and they cancel out the protons because, electrons are negatively charged, protons are positively charged, so they cancel out. So you're left with just neutrons. You're left with an atom that has no space in it. Tiny, 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 tiny compared to its original size. So that's what a neutron star is. It's an atom where the electrons have been squeezed into the nucleus and it pretty much has no empty space. So I guess you can say that if you were a star, if we could squeeze you down to a grain of sand, then we can make you into a neutron star. I guess we could say that. Okay, so this is just some ideas thing, and we talked about, by the way, last time we talked about the orbits themselves, like how to draw the orbits. We talked about the Bohr-Rutherford diagram and how to draw, the arrangement of the electrons. Okay, so any questions about this big mess that's on my screen? Nothing? Okay. All right. So, because today what we're gonna do is we're gonna go back to elements, and we're gonna talk about the periodic table. All right, which is what I have here. So this is you have a copy of this in Schoology in the Chem folder. I'm also, I think it might be also in Google Classroom. I'll have to double check. But we're going to talk about the periodic table because the periodic table is a way of organizing the elements. And we're going to talk about how, there are certain patterns to it. We're going to talk about the patterns and the trends in the periodic table. All right. Now, we're not going to cover all the periodic table. We are actually going to cover specific areas of the periodic table. We're going to cover this section here, these first two columns, and we're going to cover these sections over here, the last 6 columns. So we're not going to talk about the stuff in the middle, okay? So keep in mind, we're not going to cover all the periodic table. We're just going to look at certain areas, basically the left side and the right side of the periodic table, okay? So here we go. So here's some terminology in terms of the periodic table. The row, so the row of a periodic table is also known as the period, hence the term periodic table. So the row of my periodic table is also called the period. Now, this came up last time because last time when we talked about, you know, writing out the number of electrons that you would get, you know, and how to organize them. If you recall, the row number was important because the row number actually told you how many rings there are, right? So for example, if something is in the first row, it has 1 ring. If it's in the second row, it has 2 rings. And if it's in the third row, it has 3 rings. And by the way, that's a very simple picture of how electrons are actually organized. In truth, it's actually way more complicated than that, okay? But whenever you learn something for the first time, you gotta learn the simple stuff, right? You can't go into the really complicated stuff. So, you know, it's kind of a bit of a lie saying that the row number is the, I mean, it's true initially, but as you go down, the row number actually does not really determine the number of rings anymore because it's actually not rings anymore, to be honest with you. But you'll learn more about that if you do like grade 12 chemistry, which is like 1,000 years from now. So I wouldn't worry about it. At this point, we'll just, you know, simple picture, row number equals number of rings in the electron. Okay, so the row is the period. The column, so going this way, so these are the columns. So here's the first column. This is the second column. This is the last column. This is the second last column. Okay, these are your groups or families. Okay, so the column, we can call them the groups or the families. And it's an important thing that it says here is that they behave in a similar way. So it's mostly true that the things that are in column 1 here, they're very similar to each other. They behave very similar way. And the things that are in column 2, sorry, the last column, you know, they behaved in a similar way. And you're going to see this idea. It's not totally true, but it's mostly true. So let's take a look at some of these columns or families or groups. Okay, so here's the first one. The first one is column 1. Okay, so column 1 is, you know, hydrogen, lithium, Na is sodium, K is potassium, all the way down. That's column 1. They're called the alkali metals. All right. By the way, that's another important thing. The metals are like down, if I remember correctly, something like this. So see this staircase? This might not be 100% accurate, but pretty sure this is right. That anything on the left of the staircase, those are all metals. Okay. Anything on the right? Oh, sorry. I missed aluminum. So I think it's more like that. I'll have to double check, but aluminum is definitely a metal, so that was a mistake. Let's fix that. Yeah, so it probably looks more like that. Anything on the left of that staircase would be metals. So for instance, we have, here's iron, here's nickel, here's copper, here's zinc, aluminum's a metal, okay. Tin, that's not tin, tin's over here, that's tin, that's titanium, I believe. These are all metals, okay? But even the metals are divided into groups. So the first group, called the alkali metals, and it says that they're very, very reactive. Here's a picture of, for example, one of the first airships. They actually used initially hydrogen because hydrogen is very light. So to make an airship fly, you need material in the airship that's very light, lighter than air, so that it floats. You know, think of like a helium balloon, right? Helium balloon floats because helium is lighter than air. But they realized that hydrogen is very reactive. So the problem with using hydrogen in an airship is if ever you have an accident, it's going to be a really bad accident. Now, it says that column 1 is very reactive. So let's see if we notice something about column 1. So hydrogen if you remember, hydrogen, when we drew the Bohr-Rutherford diagram, hydrogen has one electron in the outer shell, okay? The same is true for lithium. You'll notice that here's the Bohr-Rutherford diagram for lithium. It has one outer electron in the last ring. And sodium also has one outer electron in the last ring. What's this picture here? It says hit, I'm hit, I've lost an electron. Are you sure? I'm positive. You get the joke? Not that funny, eh? So here's potassium. You'll notice that it also has one electron in the outer shell. Now, the outer shell of an electron of an atom is called the valence shell. That's the outer shell. Okay. So what all column 1 has in common is the outer shell, the valence shell, all has one electron. Okay. So they all have that in common. Now, it says that column 1, so there's the term valence shell, says that column 1 is very reactive. Okay, now why are they very reactive? It's because they have that one electron in the outer ring, they all want to lose it. Okay, having one electron in the outer ring makes them unstable. In fact, if we compare them to the last column, I'm going to show you the last column, okay? So the last column is, where is it? Here, the noble gases, okay? So this is all the way on the other side of the periodic table. Now, so if I go back to the picture of the periodic table, column 1 is the alkali metals, right? On the other side, the last column is the noble gases. Now, it says that column 1 is very reactive. Now, it says here that, where is it? Sorry, all the way down here. It says here that the noble gases are very stable. Okay, it's interesting. So this is stable. Now, why are they stable? It's interesting because, so what do they have in common? Well, helium, if you remember we drew helium. Helium has 2 electrons in its outer shell. It only has one shell, so the one shell is the outer shell. Here's neon. If you remember when we drew the Bohr-Rutherford diagrams, there was a rule that said in ring 1, the maximum number of electrons was 2. In rings 2, 3, and blah, 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 the max number is 8. Okay, so if I look at neon, neon has 8 electrons in the outer shell. There's 8. If I look at helium, it has 2 in the outer shell, but the outer shell in this case is the first. If I look at argon, you'll notice that it has also 8 electrons in the outer shell. So, is there a trend here? It's like there's some piece of information that's important. And the answer is yes. The reason why they're stable, this is really important, is because the outer shell is full. It's full of electrons. If you follow the rules that we talked about last time, the outer electron, the first ring can only have 2, and that's what helium has. And the next rings can have maximum 8. So what the last family has in common is the outer shell is full, and that makes them stable. If I go back then and compare it to the first group, the alkali metals, they have an outer shell that's, you can see, it's got 1 electron. So lithium's got 1, helium's got 1, sodium's got 1, potassium's got 1, and it's said that they're unstable. So what they want to do is they want to become stable. Now, the way alkali metals become stable, well, I'll mention hydrogen in a second. is to lose that electron. If lithium could get rid of this electron, then it would be stable because now this shell has no electrons, and this ring, which is ring number 1, has a maximum of 2 electrons, which makes it stable. This makes lithium just exactly the same as helium, if lithium can get rid of that 1 electron. If I look at, for example, sodium, right? Sodium's got the first ring is full, the second ring is full, but the third ring has 1 electron. If it could get rid of that 1 electron, if we can eliminate it, then that atom now becomes stable because now the next ring, which is ring 2, is full. And remember, a valence shell that is full is stable. So if sodium can get rid of this 1 electron, then the next ring is full and it's stable. And now sodium, which would have only 10 electrons, would have an arrangement of 2 in ring 1 and 8 in ring 2. And it would look exactly the same as neon, right? 2 in the first, 8 in the other, which makes it stable. And so that's a huge idea when we're looking at these, is that all these families want to be stable. They want to be like the noble gases. So they want an outer ring that's either full or empty. Those are your 2 possibilities, full or empty. So if I go back then to, for example, lithium, if I could empty out that last ring, get rid of the electron, then the ring below it, ring 1, is full now. So there you go. Now lithium is stable. Hydrogen is a bit funny. Hydrogen go both ways because if the rule is full or empty is stable, then you could see that hydrogen can do one of 2 things. Hydrogen can either add an electron, sometimes it does, that will make it stable, or the other way is to just get rid of the 1 electron that it does have, and in that case, it's also stable too. So if we look at, if that's a little bit confusing, let's see the next family. Maybe it'll make a little bit more sense. So look, the next family is the second column, called the alkalines. So this is now a group that includes beryllium, magnesium, calcium, and so on, right? Second column. So what do they have in common? So if you notice, the alkalines in the outer ring have 2 electrons. So this one here is beryllium. It has 2. There's magnesium in the outer ring. It has 2. If I look at calcium, it also has 2. Is there a question? It says if we erase the third electron from lithium, then the charge, yes, the course, yeah, that's an excellent point. Yes, the charge does change, which actually goes back to this pretty bad joke. I've lost an electron. Are you sure? I'm positive. Yeah, and it also goes to this. So if I look at this picture here, you'll notice that it says here, one of you gentlemen would mind telling me what is outside the window that you find so attractive. If you look, all of these things are members of the first family, the alkalines, all right? There's lithium over here. Let me just do this. There's lithium, there's potassium, there's rubidium, there's cesium. These are all members of the first family, okay? And you notice that they're all positively charged, see? They all are positively charged. Positive, 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 positive. The reason is because, and there's sodium, forgot to mention sodium. The reason is because if they have an outer ring, so imagine this is the outer ring and it has one electron, and they want to be stable. And the only way they're going to be stable is to get rid of that electron so they can be like the noble gases. And then they'll become positive, because if you remember when we looked at the animation, the PhET animation on how to build an atom, if lithium has, let's say lithium has two rings, here's the nucleus, right? And it has two electrons, right, in the first ring, and it has one in the third ring. You know, when it's neutral, it has 3 electrons because lithium has 3 protons. There's the atomic number, and there is the mass number. So it has 3 protons, 1, 2, 3 protons. Now, when it's neutral, it has 3 electrons, 1, 2, 3. But if it loses 1 electron, then it has more protons than electrons, which means it becomes positively charged. So absolutely right, Amita. The charge changes. If it loses electrons, they become positively charged. And the way you figure it out is if they lose 1 electron, then they become just simply plus. And that plus means +1. If I look at the next group, the alkalines, you'll notice they all have 2 electrons. So here's 2. Sorry. There is 2. 1, 2. If I look at the next group, the next member in the group, calcium, you'll notice it also has 2. It's really tiny over here. There's 1, 2. So they want to be stable. They have to get rid of 2 electrons. If magnesium gets rid of 2 electrons and empties out that ring, then the ring below it is full now, right? You see, it's got 8 electrons. It's full. So it will be stable. Now, what would its charge be? Well, if losing 1 electron gives it a charge of just simply plus or +1, then losing 2 electrons would make it actually +2. It's actually written like this, though. You'll see it written like that in chemistry. But it's actually +2 because it has lost 2 electrons. But it's stable now. That's family 2, okay? So we've covered family 1, and now we've just covered family 2. Family 1 and family 2 have something in common. They both want to get rid of electrons, right? Family 1 wants to get rid of 1. Family 2, the alkalines, wants to get rid of 2. If we move on, then there is group 13. So group 13 is actually this group right here. So this is group 13, okay? Now, it works for the first 2 elements, what I'm going to tell you, but then it doesn't work as we go down, okay? So just keep that in mind. We're giving a simple picture of how this works. There's always going to be some exceptions, okay? So group 13 would includes the 2 boron, and these are just some jokes. There's oxymoron, sodium boride. Hey, did I ever tell you about the time that sodium boride getting boring? I know, it's terrible jokes. And aluminum. What do they both have in common? What do aluminum and boron have in common? If I look at the outer ring, you'll notice it has 1, 2, 3 electrons. If I go to boron, which I don't have the, okay, so we can draw it. Boron, here's my nucleus, would have 1, 2 rings. The first ring would have 2 electrons. Its atomic number is 5, which means it has 5 protons and it has 5 electrons. 1, 2, 3. Okay, so what does it have in common with aluminum? It has 1, 2, 3 electrons in that valence shell. So they want to be stable. All right, now they can do the same thing that the alkalines and alkali metals can do. They can lose the electrons, but they would have to lose 3 though. Boron would have to lose 1, 2, 3 to be stable. It would have to gain a charge of +3. If I look at aluminum, it would have the same, because it's in the same family, it has the same problem. It would need to lose 1, 2, 3 electrons to become stable, +3. Now, you could ask, well, if the rule is full or empty, then can't they add 5 electrons, right? Can't they make the shell full? I have 3 here. Can't they make it 4, 5, 6, 7, 8? I guess, but problem is that, nature is going to want to pick the simplest thing. It would be a lot easier to get rid of the 3 electron as opposed to gaining 5, right? That would be harder to do. Okay, if we look at the next group, which is group 14, group 14 is carbon. Now, another thing that you may have noticed, that it said that group 1 was very reactive. And then it said that group 2 is fairly reactive. Now, it didn't say anything about group 3. So I would imagine group 3 would be kind of reactive, somewhat reactive. Group 4 is actually very, very stable. Here's an example of a member in group 4, carbon. Carbon can exist in different forms, like the graphite in your pencil, not lead. So there's no lead in your pencil. It's actually graphite. Okay. It can also be rearranged to form diamonds. So diamonds and graphite are actually made up of the exact same thing. Can you believe that? The stuff that makes up your, the stuff in your pencil that allows you to write, and the stuff that you put on your ring, a diamond worth thousands of dollars, actually the same material. Just the atoms are, just the way the atoms are arranged is different. This group also includes silicon. All right. Now, what do they have in common? This group has 4 electrons in the outer shell. Now, remember, full or empty is what these atoms want so they can become stable. These two are right in the middle. So there tend to be stable elements and not reactive at all. Carbon and silicon, they're not like, they don't really do much. They'll form compounds with other things, but they're not as reactive as the elements in the first and second column. And that's another trend that you will see. So if I look at group 13 and 14, they're not that reactive. 14 especially is not very reactive. Next group is group 15. This is nitrogen, as an example. You'll notice that the outer ring has 1, 2, 3, 4, 5 electrons. If I look at, this is phosphorus, you'll notice that it has the same 1, 2, 3, 4, 5 electrons. So they're closer to being full than empty, right? Because to empty, they would need to lose 5 electrons, but to fill up, they would only need 3. So these members tend to gain 3 electrons. And that would then give them a charge. If they were to gain 1, 2, 3 extra electrons, that would give them a full outer shell. So that would make them like -3. So, kind of similar to group 13 in that it's the same number, it's 3. The difference is group 13 wants to lose 3 electrons, whereas group 15 wants to gain 3 electrons. So if we go to the next group, which is group 16, it says that group 16 is fairly reactive. Fairly reactive. So that term came up before. Fairly reactive came up when we looked at group number 2, which was right here, fairly reactive, group number 2. So let's see what they have in common. If you remember, group 2 wants to lose 2 electrons to become stable. If I look at group 16, okay, they have in their outer shell, the valence shell, they have 6 electrons. So for them to be stable, they need 2 more. If I can gain 2 more electrons, oxygen now will have 8 electrons in its outer ring. Now it will be stable. So it wants to gain 2 electrons. In other words, it wants to gain a charge of -2. Now, if I look at sulfur, it's in the same family. This is group 16. And you'll notice it has 6 electrons in the outer ring. There's 6. So it wants 2 more to make it 8. It wants to gain a 7th and an 8th electron. It also wants to be -2. So what does group 16 have in common with group 2? So if the number is the same, in group 2 wants to lose 2 electrons. Group 16 wants to gain 2 electrons. Both groups are fairly reactive. There's a clue there, something important. If I look at group 17, which is now this one has a name, they call the halogens. It says it's very reactive. I should write the word very reactive. That should be familiar to group 1, because if I compare group 17 to group 1, so if I go back all the way to group 1 was very reactive. So where are we now in the periodic table? Well, here's group 1, right? Group 1 is right here. These are the alkali metals, right? Here we go, the alkali metals. Did I say alkaline or I meant alkali metals, all right? The alkaline's the next group. And these are the halogens right over here. This is group 17. These are the halogens. Now, both are very reactive. So what do the alkali metals and the halogens have in common? Comes down to 1 electron. Group 1 wants to get rid of 1 electron. Group 17, or the halogens, want to gain 1 electron. If I look at the the diagram for fluorine, you'll notice it has 1, 2, 3, 4, 5, 6, 7 electrons in its outer shell. It wants 1 more. It wants to gain 1 electron. It wants to be -1. If I look at, for example, chlorine, same thing. Chlorine has 7 electrons in the outer ring. 1, 2, 3, 4, 5, 6, 7. It wants to gain 1 electron. It wants to be -1. So there's something there, right? Because if group 1 wants to lose 1 electron and group 17 wants to gain 1 electron, and they're both very reactive, and group 2 wants to group 2 wants to lose 2 electrons, and group 16 wants to gain 2 electrons, and they're both fairly reactive, it tells you something. It tells you that the closer an atom is to being empty or full, the more reactive it is. So group 1 wants to lose 1 electron. Group 2 wants to lose 2 electrons. So group 1 is more reactive because it's closer to being empty. If I look at group 17 wants to gain 1 electron, and group 16 wants to gain 2 electrons. Group 17 is closer to being full, so it's more reactive. That's another trend that you do see in the periodic table. The bottom line is they all want to be like the noble gases. So going back then to the noble gases, helium, neon, argon, what do they all have in common is that they all have a full outer shell. And that's what the other elements want. But then what about things like in the middle? Like, for example, if I go back to silicon or carbon, I mean, they're right in the middle. So they're not close to being full. They're not close to being empty. They're like literally right in the middle. So what about them? What do they do? Well, it turns out that, what we're talking about today is a simple picture of the periodic table. We're talking about things trying to be stable by doing one of two things. Losing electrons, right? Or gaining electrons. But that's not the only possibility. Another possibility, which we'll talk later, is to be stable by sharing electrons, okay? Yeah, I heard it. You heard it. Sharing electrons. That is a totally different scenario, which we'll talk about another time, okay? I think we can so if we take a look at some of these questions, we talked about this, which groups are fairly reactive and which groups are very reactive. So if you remember, the trend is group 1. So groups 1 and 17. Group 1 are the alkalis, and group 17 are the halogens. They are very reactive, whereas group 2 and group 16, whereas group 2 is the alkalines. Group 16 is the group that includes oxygen and sulfur. These are fairly reactive. Which group is stable? That's the noble gases. These are stable. And what is the connection? Can't spell connection between the number of electrons in the last and outer shell and its reactivity. And the answer is the closer to being empty or full, the more reactive. Okay, and if it is empty or full, it's not reactive, it's completely stable at that point. Okay, so there's a rule, it's called the stable octet rule. That's actually what we've been talking about, although I never called it that. I don't really like the term because it implies that you need 8. But if you remember, helium has 2 electrons in its outer ring and it's stable. But the idea is that the outer shell has to be full or empty for it to be stable. Okay. Otherwise, if it's not full or empty, the chemical is reactive. Okay. And like we said, if it's close to being empty, then it's going to become positively charged because it's going to get rid of electrons. It could be like if it has 1 electron in the outer shell, it's going to become +1. If it has 2 electrons in the outer shell, it's going to become +2. And if it's close to being full, it's going to want to become negatively charged, right? It's either going to become like -2 or -1, for instance, if it picks up 2 electrons or 1 electron. That's it. Let me stop the record. That was quite a bit.